Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software RFEM as well as our standalone CFD wind analysis program Rwind. The topic for today's presentation is Rwind 2, Calculating Wind Loads with CFD Simulation. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions you may have. They're both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So as far as the content over the next hour today, I do want to begin with several CFD advantages, especially with consideration to the design standards such as the ASCE 7 and the NBC. I'll then show you a few verification examples that we have available, comparing Rwind 2 results to these standards. We'll talk about some new features and available options that we have recently released in Rwind. And finally, the majority of our presentation today will be a wind simulation example utilizing Rwind for the silo structure that you see over here on the right-hand side. We'll take these wind loads and we'll integrate them back into our FEA program RFEM, where you can carry out the full structural analysis and design. So a very common question when it comes to computational fluid dynamics is the role that it plays with the design standards. So we know that engineering codes such as the ASCE 7, the NBC, the Euro code, and so on provide minimum engineering requirements and loads for safety considerations. And of course, wind is included in this. When we look at the ASCE 7 in particular, there are 3 approved wind load methods. The first is the simplified method. So this should really be carried out for simple, symmetric, and short structures that really have no unique environmental factors. Then we have the analytical method. So this is for structures that fall outside that simplified method, but are still considered regular. And finally, we have the wind tunnel method. So this is going to be for all other structures that are considered irregular. And you'll notice here that CFD is not included in this list. So we might be wondering, well, how can it still be used while abiding by the standard? So on this next slide, I want to lay out a few benefits and advantages that we can find when carrying out a CFD analysis. But essentially, a program like Rwind is a very cost-effective engineering tool for many useful applications. And I put a lot of emphasis on the word tool here because we're by no means suggesting that this program should take the place of the requirements within the standard, but how can we use this in addition to the standard? So we know that codes such as the ASCE 7 and NBC only provide minimum wind loads. It could be in certain scenarios that we need to increase these loads due to special cases, so primarily for complex structural shapes. Now, we also can use CFD for structures that fall completely outside the standard with no minimum guidelines to follow. So the code is certainly very clear on many different types of structures, but when we get outside of these provisions, we're making a lot of guesses and assumptions. So we can use CFD to ensure that those guesses and assumptions are correct. We can assess the varying wind loads very early on in the design process. We can simply take our structure, put it in this numerical wind tunnel, and adjust that design again very early on based on these applied wind loads. A program like Rwind can also consider the surrounding terrain and object consideration. So if we have very complex hills or we have adjacent buildings, which is what we'll take a look at today, these are all going to affect the wind flow. Now, there are certain coefficients within the standard, but these are all generalized. So if we wanted a more in-depth study of those wind analysis, we could do so. We can determine the occupant comfort with the applied wind loads. So we want to look at our structure, what it's going to be used for, and are occupants inside going to be comfortable with these wind loads? Now, ultimately, if a true wind tunnel test does need to be carried out, you can imagine the cost and time savings that we could have if we were to initially run the CFD analysis to adjust our design, whether it's under design, over design, before we're spending the time and the money to do so with that true wind tunnel test. So overall, CFD methods should be used for complex structures with no standard guidelines. We're not suggesting to use a program like Rwind for a box type structure. The code is very clear on the wind loads to apply for those type of structures, but rather when we kind of get outside of those specific categories, we can use something like CFD. And lastly, taking the extra step for the project wind analysis. So when you're able to save these various images with wind pressures, or for example, the video that you see here on this slide, you can include it in a digital calculation package that you're submitting to your client. This will certainly help you stand out against the competition when you are, again, taking that extra step to show that you have assessed the wind loads on this complex structure. Now, with that said, we do have some verification examples available on our website, and my colleague has put these together. And you'll notice that the PDF, which is included in this GoToWebinar, has hyperlinks directly to these verification examples. The first, if we go ahead and click on it to take a look, is going to compare the ASCE 7 2022 standard with Rwind for a general box type structure. So we thought it might be interesting to compare these two to see how the Rwind results match up to the code standard. And you can see the output and the deviation within this table, as well as within this graphical format. In a similar manner, we also have a verification example here with the NBC 2020. So taking a look at this particular verification example on our website, what you will notice is that this is for a dual pitch roof here. And we're also, of course, going to compare the analytical calculations from the NBC to Rwind, but also this one was carried out in a true wind tunnel test in Japan. So with this verification example, if we scroll down here, we will see those three methods compared in graphical format: the NBC 2020, the experimental wind tunnel, and Rwind. Now we have many more verification examples available on our website, comparing to Eurocode, as well as other analytical calculations that you can access with this third link. So for those of you not familiar with Rwind 2, we now offer two versions, the basic and the pro. So we have this table here comparing the features that are available within each version. And we won't have time to go through each one of these today, but all of these do have hyperlinks as well that go directly to our online manual for Rwind to discuss a little bit more. But the main focus here is going to be up at the top, our first line, this steady flow calculation, which is offered in both the basic and the pro. And this is essentially going to capture the wind flow at a single point in time. But you'll notice on this second line that we also offer the transient flow calculation within the pro version. So we can actually see how the wind flow varies over set time steps. So you can almost think of this like a time history analysis. It also features a more advanced turbulence flow model that's shown in this fourth line here. And ultimately, this transient flow is going to capture phenomenons for tall, slender structures that we might see, such as vortex shedding. Now, we're only going to be focusing on the steady flow for today's presentation, but if you are interested in the transient flow, I did carry this out in a previous Rwind 2 webinar that you can find on our website and our YouTube channel. Now we'll take a look at several of the new features that we have released within Rwind 2 in the past several versions. And I'll preface that each one of these features here we'll actually be looking at in our example today. So we'll begin with the wind tunnel size. We offer now new scaling options. So the tunnel for the numerical wind analysis, the dimensions are set as small as possible for short calculation times. So it could be that the solution does not converge, requiring us to manually extend the tunnel length, for example. Well, now we offer new scaling options once we are within Rwind that I'll show you in our example today. Also, within the Pro version, we offer permeable surfaces. So this allows wind flow through the surface itself. And we would input information like the Darcy coefficient, the inertial coefficient, and porous media length. Now, this might be important for something like fabric structures or permeable scaffolding to allow some of that wind flow to pass through the actual surface. We can generate zones from the RFEM 6 surface numbers. Now, again, this will make more sense as we get into our wind, but we use zones for not only the input, but also to interpret our results. And previously in our wind, we had to manually create these zones. Well, now at the click of a button, we can actually generate the zones automatically, which you'll see over here on the right-hand side, based on the surface numbers within the RFEM model. Furthermore, with these zones, we can adjust the load factor to scale these wind loads up or down. So perhaps we complete the R-wind analysis, we want to scale up particular areas of the structure. You'll see that reflected with the wind pressure, not only in our wind, but also when we take these loads back into RFEM for the analysis and design. We can also display the R-wind results graphically in RFEM 6. So just a nice feature that potentially you don't even need to open up R-wind at all. You can actually carry out the calculation and view your wind pressure results directly in RFEM. The static analysis with wind tunnel loads from experimentally measured pressures. So this one's quite interesting in the sense that we can take experimental data. So if we have taken this structure and put it in a true wind tunnel test, or we have analytical calculations, we can now distribute this pressure manually on the structure, but we'll take advantage of the CFD mesh that's created in our wind. And for this, we have two interpolation methods, including diffusion and Gaussian. And ultimately, this allows us to compare the experimental data with the R-wind results. We can also take this a step further and use the experimental data in the static analysis if we prefer to not use the R-wind. Again, we'll cover this at the end of our example today. And finally, the R-wind trial has now been extended to 90 days. So this lines up well with our RFEM trial version that is also 90 days. Both programs will be full capability over this duration. Should be known though that with R-wind, we have a limit of 20 calculations. So if you are exceeding that or getting close to that, you might consider buying the full license at that point. Okay, so let us begin in our FEA program RFEM here. And we can use R-wind as a standalone program. So I do want to make note of that. But for today's presentation, we will be integrating the structure into R-wind and then integrating those wind loads back into RFEM. For those of you who have joined us for webinars before, this structure may look familiar. I did a previous webinar on the silo structure design where I fully modeled this structure. I carried out the analysis and the design of the members according to AISC, as well as a general stress design for our surfaces. So we won't get into that portion today. We're only going to focus on the wind analysis, but you can certainly take a look at that webinar if you are interested in that. So let's take a look at a quick model review though. So going to our navigator here, we have our silo structure and you can see these surfaces are defined here with stainless steel. We also have A53 grade B pipe members supporting the structure at the bottom. And then we have a couple ring beams, A36 material, as well as these channel sections spanning in between the ring beams. Now, in the previous webinar as well, I had also applied various loads. So we have 3 simple load cases for today. The dead load is only going to include the self-weight, so no additional loads applied here. However, if we take a look at the pressure in the horizontal direction, we want to account for some type of fill load inside of this silo structure. So you can see that outward pressure along the body of the silo up here close to the top, but not quite to it. And then as well as in the hopper, we also have a friction load here for, again, that fill. So it's going to be in the downward direction along the full height of the hopper as well as the full height of the silo. So now we want to begin with our wind load. And when we go to the base data, which we could right click on the model name to access that dialog box here, or we could access it within our quick tools. This would be the dialog box that pops up when we first create our model. But we can revisit it here under the second tab to take a look at all of the various add-ons available. So again, for those of you not familiar with RFEM, we do work with this add-on concept in the sense that RFEM is the base FEA program that provides the modeling, BIM integration, and the full analysis. But if we want to take it a step further and carry out the steel design according to AISC or concrete design and so on, or advanced analysis like dynamics or stability, we would need these add-ons. So you create the package that's specific for your design needs. But you'll notice here that we also have wind simulation. So this is telling the program that we now want to integrate this model with the standalone program Rwind. Under the third tab, we will generate our load combinations automatically according to the ASCE 7, the 2022 standard, but more importantly, specific to Rwind. We will generate our wind load profile according to the ASCE 7, the 2022 standard is available. We also have the NBC 2020 standard available, as well as many other international codes here. Now, if we want to carry out the steel design, again, we won't be getting into that today, but the AISC 360 is available, or the CSA standard. 2016 is currently released in this version, but we do plan to release the 2022 in the next few weeks. So once we have this information input, we want to go into our load cases and combinations, and we will generate our first wind load case here, load case number 4. And we'll give this the name wind with the action category set to wind load based on the ASCE 7. Now I could manually apply my wind loads here to the structure, and in that case I would keep the analysis type set as static, but because we have enabled Rwind, we now have the wind simulation option available. And this gives us 2 additional tabs here up at the top. So moving to the second tab, we want to input the wind simulation analysis settings. This is what is going to be used in Rwind, but we have the ability to set this here within RFEM. So we do have a default definition set that we can simply modify, or we can create multiple definition types with the option down here in the lower left. The simulation type is going to be set to steady flow. Again, we covered this in the PowerPoint that if you do have access to the Pro version, you can also run the transient flow. So moving forward with the steady flow, we now want to input in the density of the air. And variables such as altitude, temperature, pressure, humidity, these are all going to affect the dynamic behavior of that fluid moving through that wind tunnel. We also have the kinematic viscosity we would want to input. This is the resistance of the air to deformation, and it's also the ratio of the viscosity to the density of the air. Several other options that we have available to turn on or off, including the considered turbulence that's by default turned on. So this will consider that turbulent flow that's characterized by chaotic changes to pressure and flow velocity. Now in turn, if we uncheck this, this would be laminar flow. So most likely we want to consider that turbulence. Now, the second option, the slip boundary condition on the bottom boundary. So the lower boundary condition at the tunnel's bottom surface is set to smooth by default, but we could check this to release the surface or to set a different surface roughness. And we might do this if we were considering the wind analysis on, let's say, the top 5 stories of a multi-story structure, and we weren't carrying out the full wind analysis for the entire structure. The consider surface roughness. If we turn on this option, we get a new tab where we can input in the surface roughness properties. This will be applied to all surfaces within the RFEM model. And I'll get back to this a little bit later on within Rwind for some additional options. The user-defined dimensions of the wind tunnel, again, we're going to optimize that wind tunnel for you, but if you do need to make changes to that, we could certainly turn on this option. Now, once we run the wind analysis in Rwind and we bring these wind pressures back to our RFEM model, we do need to distribute them to the members as well. So not only the surfaces, but also the members. And the program wants you to input here how we want the member load distribution. The default is concentrated. So this will be point loads along the member length. Alternatively, we have a uniform load, so the program will essentially average out those loads and apply it uniformly over the member length, or trapezoidal. So we'll have a couple different loads applied over the member length. Now, the finite volume mesh density by default is set to 20%. I'm going to change this to 10% just to get a quicker calculation for today. Probably 20% or higher would be the minimum that you want to go. And this is the actual mesh density throughout the wind tunnel itself. So nothing to do with the model. And we'll see this once we're over in our wind. Under the second tab here, we can set the max number of iterations. We may need to increase this if we don't get convergence. And we also have our turbulence model. So we have both K epsilon and K omega here. Much more information, a lot of theory that goes in behind this. So if you want to access that within our online manual, you can always click on this little question mark down here in the lower left-hand corner to learn more about these options. Now, the additional tabs, such as the advanced, you're probably not going to make too many changes here unless you're an advanced CFD user. So once we have this input, we now move on to the wind profile. So what is the wind speed entering into this numerical wind tunnel? And you can see once again that we do have a default option set here according to the ASCE 7, the 2022, because that is what we set in our base data. Alternatively, we can use this option here for user defined. So no longer are we referencing a specific code, but you can manually input the wind velocity here as a function of the tunnel height, including the turbulence intensity. So we'll go ahead and use the ASCE 7 for our example today, and then we have two additional options here, including the map and parameters. So what this allows us to do is to access what we call our GeoZone tool, and this is available on the Delubal website, where we have taken multiple standards all over the world and integrated with Google Maps technology. So specific to the ASCE 7 here, we would select our risk category. We could toggle here to Google Maps directly, and we could further input in the direct address, or we could click on the map. So just choosing here the address of our Philadelphia office, and we can zoom in here. We can see that the ASCE 7 has set this basic wind velocity for risk category 1 at 107 miles per hour. We can click OK, and what will happen is all of the location and the wind velocity will directly be imported in for this wind profile. Now, alternatively, we can choose the user defined, where we just simply type in, let's say, a basic wind velocity speed of 110 miles per hour. Now we can make modifications to the exposure categories such as C. We also have additional information that we need to input, such as the turbulence intensity, but also these factors that are specific to the ASCE 7 that are all going to affect the wind velocity here at the start of the wind tunnel. So now we see as a function of height and miles per hour what that wind speed will be. I can toggle here. We can see a better view of exactly the information that we're setting here. So now that we've input in this information, we also can input in the wind direction. And this is all based on the global x-axis. So if we have this set to 0 degrees, the wind flow is going to move from left to right here on the structure in the positive x-axis. Now we'll get to a little bit later on some alternative options here. We'll also discuss the experimental data at the end of our presentation today. So finally, we have our wind tunnel. Again, the program has optimized these. We do have the ability here in RFEM to manually adjust these individual input for the wind tunnel size. Now, before we are able to run this within our wind, we do want to take care of one more additional setting under Calculate Mesh Settings. So this is typically where we would input in our information for our FE finite element length within RFEM itself, and some additional options here. But we also have a wind simulation tab and some additional options here that are specific to what we call our shrink wrap mesh that is always needed with this CFD analysis. And I'll show you that once we get into our wind, but these specific settings here are going to control that shrink wrap mesh, including the level of detail. So a scale of 0 to 4, the higher we set this, the more detail we will take into consideration. What this means is that, do we want this shrink wrap mesh to take into account every single little geometric detail here of our structure, or do we want to simplify? So this is set by default to 2. We can also close openings, so we can essentially not allow wind to flow through certain areas of our model. So down here at the bottom, we certainly want the wind flow to move through these areas, but I could close them if I prefer. What would probably make a bit more sense with this is something like open doors or open windows. We can use that shrink wrap mesh to close those openings so that wind flow is not allowed to move through the interior of the structure. It should be known though that if you choose to close these openings, that the shrink wrap mesh in Rwind is not going to distribute those loads to the adjacent elements. If you do want to take that into consideration, you should apply another surface element in RFEM. And for example, we have a surface load transfer that's purely used as a surface element to transfer loads to adjacent objects without adding any stiffness. So plenty of resources on that in previous webinars and on our website. The optimized member topology, for example, if we have a W section, do we want this shrink wrap mesh to account for all of the flanges, the webs, that geometry exactly, or do we want to simplify a bit further with more of a box type structure? So again, the default here is set to something kind of middle of that scale. Down here, the keep wind simulation results of mesh is deleted. This is really helpful in the sense that if we make very minor changes to our RFEM model and the mesh here in this program deletes, we won't necessarily lose our Rwind results that could take several minutes depending on the complexity of the structure to run. If you make any major changes, though, you should use this option quite carefully in the sense that any geometry changes, the wind analysis should probably be rerun. So just keep that into consideration, but when we're swapping out materials or something, this can certainly be a useful feature. Okay, so now that we have all of this information input, we can go to calculate and we can open up Rwind directly here. So notice that the program is going to calculate the FE mesh in RFEM, and that's because our shrink wrap mesh, once we get into Rwind, does correspond with the FE mesh in RFEM so that we can bring back those loads, those wind loads, and apply them to the structure here in RFEM for the static analysis and design. Okay, so once this program launches here, what we should see is our silo structure brought into this numerical wind tunnel. So we'll cover a little bit of the input here first before we run the calculation. So sure enough, here is my silo structure. Again, only the geometry is needed. It's brought into this numerical wind tunnel. We're not really caring much about materials and stiffnesses. You'll also notice in the wind tunnel itself, as I mentioned, that mesh density. It's pretty coarse out here, but as we move closer to the structure, it's a bit more refined. And this is essentially the mesh that's occurring throughout the length, the width, the height of this tunnel. Now we talked about the new scaling options for this wind tunnel. So here in our navigator tab, we can double click this wind tunnel and we have added this scaling factors option here. So now, for example, if we know our model is not converging with the simulation, we need to add some additional length within our wind tunnel behind the structure, which would be L2. We can add a factor directly in here, such as 2.0. So when I click OK, the program gives me a warning saying I must also click the Adjust Automatically button. So we do so here, considering the model standing on the ground. And when we click OK, we should now see that wind tunnel extended by a factor of 2. So this allows us to quickly make changes to that wind tunnel rather than manually adjusting each input individually. We'll go ahead and click the Undo button. We want to keep that wind tunnel as the default size. You'll also notice that wind profile that we have set according to the ASCE 7 is shown here along with the magnitude, and that wind flow will move from left to right. So we also talked about in the PowerPoint the option for zones. So currently under the zones, we just have one option, and that's the default zone, which is going to include this entire model. Now, previously, if we go here to this second tab and I zoom in, we used to have to create these zones manually within Rwind itself. So now under the option edit, and we have here zones, we can generate the zones from the RFEM surface numbers automatically. So notice now all of these zones have been created here, and I can toggle through them, and I'll actually also turn off here the mesh edges so you can see this a little bit more clearly. But every single zone is going to correspond with the surface number that we have set within RFEM itself. So ultimately, obviously, this is used to subdivide the model into parts, but also to assign specific input properties. So for example, graphically, I can choose one of these zones here, double click on it, and we can assign a new material. So when I create a new material definition type, I can apply those surface roughness input options here. And we previously saw this option in RFEM as well, but it was applied to all surfaces. But now that we're within Rwind, we can apply different surface roughnesses to each individual zone or surface. Additionally, if you have that pro version, you can consider the surface permeability. So we have the Darcy coefficient, inertial coefficient, and the porous media length to allow some of that wind flow to pass through the surface. Now, also after we are done, we will also use these zones for result interpretation like drag forces. Going back to the model here, I also would like to take a look at this shrink wrap mesh. So we'll go ahead and activate it here under the simplified model. I'll turn off my wind tunnel, and zooming in here, you can see that again, the program has created this shrink wrap mesh automatically for us. And this is truly the huge advantage of Rwind, is that when you're carrying out a CFD analysis, it is required that you have this shrink wrap mesh, and ultimately it can be really time consuming to create this simplified model from our more complex RFEM model. But the program is doing all of this automatically for us. And again, it's needed in that CFD calculation with that open foam solver. It's also correcting any mesh errors automatically. So you'll notice that if we zoom in here, we have triangles everywhere that have to intersect perfectly with the adjacent triangle. So the program has taken care of all of that for us. It has closed a lot of these open edges. It also has deleted or simplified any unnecessary detail. Now, again, this all depends on those settings that we set back in RFEM, or we can control them here in Rwind. You can see that there's certainly some simplifications going on here, but again, that's going to speed up our calculation time a bit rather than waiting longer with taking to account more of those details. So we are now ready to run the calculation, but rather than waiting for this to run, I'm going to go ahead and open up an already saved model. So when we run the Rwind calculation, we would jump to the simulation tab here, and the run calculation option would be available. Once it's done, we're now presented with our results still here within Rwind. We are initially presented with the surface pressures. So viewing the surface pressures, we can move our mouse around and we can see the magnitude directly given. And we have the pressure acting perpendicular to the surfaces. When we rotate this around, we maybe have some higher suction forces denoted by this negative value. We can also activate the drag forces. So the drag force total for the RFEM model is shown at 15.2 kips, and we can see this again shown graphically here. But under these sections, this is where we can also take advantage here of those zones. So notice zone number 1, which is my members only, this drag force is going to update here to show me only the forces for these relevant sections. Now we could continue to do so with some of these various zones, but perhaps I'm interested in both zone 7, and I hold down my control key, zone 16 for the body of the silo structure, and I see my total drag force here as 10.6 kips. Okay, so we'll turn off those drag forces. We'll go back to the full member model here for the pressure. We can also take a look at the pressure coefficient factors, and these are going to represent the relationship between the static pressure and the stagnation pressure. So again, these contours shouldn't change from our pressure, but our magnitudes here certainly will. We then can view the pressure in and around the structure. So when we are taking a look at this option, you'll notice that we have this slicer directly through the wind tunnel. Under this clipper tab, we can change maybe in the X direction or any of the other planes available. We can also take this and kind of slide it here from left to right to see those wind pressures changing. Again, we can use our mouse to view those magnitudes around the structure itself. Same concept here for the velocity field. We can actually view the wind flow velocity in miles per hour in and around the structure. Then we have the two additional options here related to turbulence. And the first option is going to show the turbulence with respect to the kinetic energy. Again, can show the magnitudes here. Our epsilon is going to show the results of the turbulent energy dissipation. So moving on to the additional options down here under other options, we have our velocity vectors. So this allows me to zoom in here and I can actually see the magnitude and the direction of these velocity vectors and how they'll essentially affect the structure. So we can see how the velocity is either moving towards a structure or when we have that particular suction force. And finally, we have our streamlines. So this is going to show the particles that allow me to study the airflow as it moves through this tunnel. And we can adjust the streamline settings here. And under the drop down up at the top, we can change this to a segment, to a rectangle, or currently we have it set to a 3D box. Additionally, we can rotate this around and graphically make modifications here to the size of our 3D box. If we wanted to set that to something more narrow, we could rotate it. Once we click OK, this will adjust those particles and we can activate the flow animation. So this is certainly, again, something that's going to be helpful in studying those airflow particles as they move around our structure. Under tools, we can create a video file. So you can save this MP4 file to your computer. And again, this is something that could be really beneficial in something like a digital calculation package that you're submitting to your client. Okay, so moving back to the pressure, we have also the option called point probes. And when I right click here to add in a new point probe, I can set these graphically and just click on various areas of my model here, including the members or maybe the backside here to see these suction values. So you'll notice that when I set these point probes, that they are now stationary here. So this will allow me to view the pressures at particular points, or I can toggle to the pressure coefficients here. Again, those magnitudes are going to change, but these point probes are always available within the model. We can turn them on or off too with this checkbox shown over here on the right. In a similar manner, we also have what we call line probes. So I can right click here to create a new line probe. But if I try and set this graphically, the program just gives me a short warning saying, oh, can't set it graphically. Please use this alternative tool. So this tool actually resides over here where we can graph along the line probe. Now notice that we're making a slice here through the structure. We can change our slicing plane. We can set an offset if we would like. And essentially we can click on several locations here with our mouse, creating this cut right up through the center of the structure in the vertical direction. And when I'm done, I can double click and we see here, and actually I want to toggle back to my pressure, our pressure as a function of the length for that line probe. Now we see an alternative line here. This is going to be our internal pressure, maybe something we're not so concerned with, but we can certainly view this pressure along this entire height. Now when we save this, it's now saved as a line probe that we can always access here for any future results within the line probes tree option. I also wanted to point out under the View tab that if we take a look at our results, we can activate the member forces. So of course, we're looking at wind pressures on the surfaces themselves, but remember, we have all of these members supporting the silo structure at the bottom. So these member forces are given here in KIPS. This is the information that will be taken back into RFEM and applied as concentrated loads for that static analysis. All right, so now that we are done reviewing the results within our Rwind, what we would do is to exit out of the program here and go back into RFEM. We'd want to save our results essentially, but this will bring in those wind pressures into the model. Now, I do need to open up an already saved model here for my load case number 4. And I want to run the static analysis for this load case. Now I've already done so I can just simply view the results, but that does solve very quickly because we already have our wind pressures that are brought back into the program. But one feature that we've recently added once you run this calculation is this toggle now available in our navigator in this 4th tab under results called wind simulation analysis. So this allows me to view the wind pressures directly in RFEM itself as well as pressure coefficients. So again, technically I don't even need to open up Rwind at all. If I prefer, I can run this calculation silently in the background and then I can view these same pressures here directly in RFEM. Now we've also carried out the static analysis. So initially what we're seeing here is based on the wind tunnel here, which we can view the graphical load shown here within the RFEM model, and the deformation of this silo structure. So if I increase the deformation factor, just as we'd expect, we're seeing this structure deform from left to right based on this applied wind load. What else we can take a look at are the member internal forces. So we can activate here the members, we can view axial forces, bending moments, shear forces. Taking a look at the axial forces in particular, as we would also expect, we have a high tension force for this column up here at the front of the wind load, and our 3 additional columns here are in compression. We can view the results of these surfaces by activating our option here. So we can view the internal forces or we can view the stresses such as the von Mises stresses. So if we zoom out here, we can see that relatively low stresses for this wind load. Maybe the highest stresses are down here at the base of our hopper. Now that we have these results shown here for this wind analysis, we would want to further combine these into our load combination. So remember, we have these additional pressures for our fill. We also have self-weight. Well, the program has automatically generated these load combinations according to the ASCE 7. So we can take a look at here if we'd like, just graphically showing the wind load, for example, with that fill pressure along with the self-weight. And we could run the full analysis for these load combinations. This is also the point in time that we would probably want to carry out the design of our steel members or the general stress design of these surfaces. So you can do so within our additional add-ons such as stress strain analysis, the steel design add-on. Again, this is where you can refer to that other recorded webinar where I went much more into detail from this point forward with the structured design. So going back to our original load case here for wind load, we have applied this wind load again based on the global x-axis, but we know in reality that wind does not necessarily act from one direction. It can act from any of the directions. So we would want to consider additional load cases here. Well, we can do so by going back into our load cases and combinations, and we can directly make a copy of load case number 4. So notice that all of my simulation analysis types that we're seeing here, the wind profile, everything was copied from this previous load case. But what we do want to adjust here is the wind direction. So perhaps I want this to act at an angle of 30 degrees. I can input in 30 degrees. Program will ask us to delete the results. That's fine. Maybe we go into a plan view here. And now we see that this wind flow based on the global x-axis is at an angle of 30 degrees. So this is certainly important, especially for unsymmetric structures. We want to take a look at the wind acting in all different directions, and you really have the freedom to set any angle that you prefer. So we'd want to continue to do so with those load cases. However, I want to show you a user-friendly option here for this load case generation, and it's available in our navigator under the Data tab under Load Wizards, and we have here wind simulations. So this will actually generate those load cases automatically based on a specific step angle. So I'm going to set this to 30 degrees, and I would like the program to create these load cases from 0 degrees to 180 degrees. Well, now under the Load Cases tab, notice that all of those specific load cases, every 30-degree increments, are automatically generated here. So what we should see now within our drop-down box is not only the 2 load cases that we manually created, but now we have these additional load cases that the program has quickly generated for us. And taking a look at these in plan view, again, we have 0 degrees, but as I cycle through these various wind load applications, notice that my wind tunnel dimensions are automatically updated for me. And this is the information that we would want to carry out the analysis within our wind. We could, of course, bring it back here into RFEM and notice that the load combinations were automatically updated as well to consider those different wind directions. So going back to our original load case here, another topic that we would like to discuss is adjacent objects. So again, the code does have some coefficients or recommendations for when we do have adjacent objects, but for anything more complex, we would perhaps want to take this into consideration in our wind directly. And for my example today, I have this silo structure, and this is the structure, of course, I'm interested in designing, but perhaps there are the identical silo structures placed very closely to this one that I know are going to affect my wind flow. So what we can do here is to take this model and to go to File, Export. And I can export this model as an IFC file. So I would go ahead and carry that out. I can save this IFC file directly to my computer. Then I can immediately, in this same RFEM model, go to File, Import that IFC model that I just created. Now I went ahead and did so already for this example. So we can select this IFC file that we have created from exporting this silo structure. And I can either graphically select a point here to import in the IFC, or I can input in the coordinates directly. So we'll begin with the coordinates of -29 in the X, 14 in the Y, and 0 in the Z, which is our elevation. When I click OK, what we should see here is this IFC structure generated. Now, IFC objects are not anything that we're designing here within RFEM. We could right click here to convert into surface models with stiffnesses and materials and thicknesses, but I'm really just using these objects for the wind analysis only. And we get a 4th tab here in our navigator where we could quickly turn on and off these IFC objects, but ultimately it's really not going to influence the static analysis and design only once we get into our wind. Now I'm going to do the exact same thing here by file importing in that same IFC file. So we go ahead and select it from our saved location on our computer. And the second coordinate point that I'm going to put in here is again -29, but this time I'm going to modify this to -14 and 0. And I click OK, and what we should see is our additional silo structure. So now we have these closely placed structures adjacent to each other. And when we turn back on our wind flow, again, based on the global x-axis, there's no doubt that the wind flow will certainly be affected in this scenario. So before you export out to our wind, under the calculate mesh settings, it is important here that if you do have these IFC objects you want to take into consideration in our wind, under this wind simulation tab, we do need to activate here the export of all IFC objects, or you could graphically select which ones you would like to export. So that is something that you should take into consideration. So now that we have taken these IFC objects, insert them into the RFEM model, before I go into our wind, I also want to discuss our last major point here, which is the topic of experimental data. So for now, I'm just going to totally hide these IFC objects. They still exist. I just graphically turn them off. And we will assume that for this particular silo structure that we have taken it and run it in a true wind tunnel test, or it could be analytical calculations according to the ASCE 7, whatever it may be. And we're wanting to compare these results to what our wind is coming up with. So we can do so within this load case number 4, our original load case. Under the wind simulation tab is the option here to define experimental data from the wind tunnel. So when we activate this option, we now get a 4th tab here. And this requires some points to be input where I can compare them ultimately to my experimental data. Now, in order to populate these wind points, what I would suggest doing is under the option types for surfaces, we have this feature here called additional surface result points. And originally with the model, I created some nodes here. And for my example today, they're pretty random just for example purposes, but you'll notice that we have a node here along the hopper, kind of at the midpoint. I also put a node here spanning in between my ring beams. I have an additional node here and also one at the top. So this represents the points that I would like to tell the program to compare to our wind from in comparison to my experimental data. Now, in reality, if we have a wind tunnel test, analytical calculations, we would have many, many more points than just these 4 points. But for example purposes today, we'll just use these 4. So under the types for surfaces, additional surface result points, we would right click here to either edit this option or to create a new result point. Now, I've already taken the liberty to do this, but you can easily create a new point in the lower left-hand corner, and then you can graphically select an existing node here on the structure, or you could input in the coordinate points yourself. So I have created these 4 points, again, just graphically selecting the 4 points that I showed you here on the structure. I've also activated this option here, surface probe for wind analysis. So this is important as well. So now once we have input in this information, what you'll notice here under load case number 4 in my experimental data, that these 4 points are automatically populated. They're exactly what I set back here in the surface result points. But now I want to tell the program, what is my experimental data? What is the pressure that I found, outside of something like our wind, such as a true wind tunnel test or analytical calculations? So we can begin by setting this first point at the bottom hopper to 10 pounds per square foot. And then the 2 points located along the silo body, we'll set this as 40 pounds per square foot, so 0.04 kips per square foot. And finally, at the roof, this point up here at the top, we will set a small suction force of 0.005. Again, completely arbitrary, just for example purposes today. We also need to limit these pressures to specific surfaces. So we don't necessarily have to choose just one surface. We can choose multiple surfaces, but in reality, when we have multiple points, these are probably going to be acting on single surfaces. Well, I've already defined this information here with the surface result points. This was a requirement here. So it's very easy to select these here, hit Control C, select my column cells here, hit Control V just to copy and paste. Now, what else you'll notice is the interpolation methods available here. So the first is the diffusion, which is by default. This is essentially going to distribute data from the source point over the surface. And this is going to interpolate only on one side of a surface. So really good for open type structures like canopies, for example. Now, alternatively, we have the Gaussian method, and this is going to interpolate values around the source point in 3D. And this is going to be better for closed structures rather than open because it influences both sides of the surface. So something more like a building, or in our case today, this silo structure would be fine. There are 2 options here with Gaussian, including the user defined, where we choose the radius that it will integrate itself. So for this example, I'm setting the radius to something very large, such as 20 feet. This will make more sense once we get into our wind. So just bear with me here. But once we set this interpolation method, it is applied to all points. So now that we have these points defined, and remember, we still have these IFC objects in the background, we would want to open up the Rwind model by going to calculate, open Rwind here, but I'm going to open up an already saved model. So we'll go ahead and launch this because I have already carried out this calculation that takes just a couple minutes or so. So what we should see is a very similar structure to before, but this time I would hope that we would see the IFC objects also taken into consideration. So sure enough, once we open up Rwind, we now see here our original silo structure that we're interested in, but we also have these IFC objects. And not much, wind tunnel has been adjusted, everything automatically. So what we would like to do here is to run the calculation. And I've already done so. So under the simulation, I thought it might be interesting just to view how the results just slightly differ from our single silo when we have taken into consideration these additional silos out in front. Notice that even for IFC objects, we can view the pressures on these in Rwind, but mainly we're interested in, of course, the pressures of our rear silo structure here. If we take a look at the streamlines, we can go ahead and activate these here. And we can make modifications to the streamline settings by graphically maybe narrowing this 3D box here inside these 3 silo structures. Maybe we increase the height. We click OK. We can activate the flow animation here. So now we can see how these particles may be deflected by these front 2 silos that might increase the pressure here for our rear silo, but perhaps the side pressures decrease due to this deflection as well. So going back to the pressures here, under the data tab, remember how we have just set those points back in RFEM for the experimental data. These are now inserted here as point probes. So you can see those 4 point probes given to me at those particular locations, and they're available here within my navigator. And under my sections tab, I'm going to go ahead and only activate here the RFEM model so that we don't need to worry about the view of those additional IFC objects. But currently those point probes, again, the same points that we generated in RFEM, are just showing me my pressure from the Rwind analysis. But now under the View tab, we can expand here the results, and under Surface Quantities, Verification Data, we have the additional options here to activate the verification data for the verification points that we have set within RFEM. So this should look much more simplified. Notice we have 10 pounds per square foot, 40 pounds per square foot for the body, and that 5 pounds of uplift up at the top. Again, in reality, we would have many more points here, but the program is going to transition from that experimental data that it's given, and we have 0 set for the rest of these points. So going back here to the data tab, what I'd like to point out is that if we double click on these point probes, we have the same options available here to modify these interpolation methods. So this is the same information we saw in RFEM. Notice that my radius is set at 20 feet. Well, I could set this here if I'm interested to something much smaller, like 2 feet. So I click OK and I click Apply. So now you can see what I mean here, that if we set this radius to something much smaller, we're only going to be interpolating the experimental data over this very small area. So that's why I set it to something extremely large, such as 20 feet, to cover this entire surface. If we have multiple points, though, we probably do want to use something much smaller so that the program can use that shrink wrap mesh and interpolate between that experimental data. So going back here to the 20-foot radius, and I click OK, we should see that change. Back under the View tab, what we can see here is the actual difference now between the Rwind results versus my experimental data with these point probes. So this magnitude that's now shown here with these point probes is showing me the pressure difference in those 2 methods. So this, again, can be really interesting for us in comparing to the Rwind results very quickly, very easily to something like a true wind tunnel test or analytical calculations. Now, exiting back out of Rwind, and we go back into RFEM here, the final thing that I just wanted to point out is this last feature to use the experimental data for the static analysis. So if I am not interested at all in using my Rwind wind pressures that we've calculated with that CFD analysis, rather I want to use the experimental data for my static analysis, we could do so with this checkbox here. We still have to carry out the Rwind analysis. The reason why is because we use that shrink wrap mesh to interpolate between all these experimental data points, just as I showed you within Rwind. So again, the calculation is still needed, but the results of Rwind is no longer important because we're purely going to refer to this experimental data here within the RFEM calculation. So just something I wanted to point out further. Okay, so that will conclude our webinar today. So we'll go back to the PowerPoint here. This webinar was recorded. It will be placed on our website on the same webpage that you registered for this presentation, usually within the next day or two. You can currently download the model that I used for the presentation as well as the PowerPoint. I encourage everyone to download the free 90-day trial version of both RFEM and Rwind if you're interested in this further. Again, open up this model used in the presentation to take a look yourself. If you have any questions about today's presentation, you can reach us, shown here in our Philadelphia office at the bottom of this slide. Our phone number is 267-702-2815. Our email is info-us@duluwal.com. So we will have many more upcoming webinars. You can register at duluwal.com under support and learning webinars. As most of you know, I will send out a reminder email about a week before these take place. So keep an eye out for those within the next coming month. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So it is a requirement of the states that we are pre-approved providers that you're here for the full 60-minute duration in order to receive that PDH. Now, if you watched with a colleague or you watched in a conference type setting and you yourself did not register for this GoToWebinar with your own name and your own email, but you were here for the full presentation, we'll be happy to issue you PDH. Please send us an email requesting this at info-us@duluwal.com. Let us know who you watched it with, and in turn, again, we will send that PDH to you. Also, the PDH certificates are not automatic after this webinar ends. It usually takes 1 to 2 days and it will be sent in your email. So again, keep an eye out for that. With that said, I want to thank everyone for attending, and as always, we hope to see you at the next presentation. Thank you.